All right, good. So I'm going to talk about something completely different, but also somewhat relevant. So basically, how do we get that, which is the closest image ever taken of a Kuiper-Belt object? So I work on New Horizons, which is a NASA mission that was launched back in 2006, flew past Jupiter in 2007. We didn't even barely look at Jupiter, and then just kept on going. And you probably heard about us when we flew past Pluto back in the summer of 2015. I came on the mission like around here. So, you know, after all the wait, and then right around here is when we started looking for what we would do out here. So this is, Earth is like there, very close in. And then we got a kick from Jupiter and then came out. And you can see there's not really much inside of the orbit of Neptune. The giant planets just clear things out. It's just dynamically unstable there. But once you get beyond Neptune, there's a lot of stuff out there. And we call this broad area the Kuiper Belt. But specifically, there's parts of the Kuiper Belt that are formed much closer into the sun and then got thrown out. Pluto is a case of that. Pluto formed basically where Uranus is now and then got shoved outwards by Neptune. But there are some objects that their orbits are just basically nothing's happened to them. So after Pluto, that we wanted to fly past one of those objects. And when we got funded for the mission, the assumption was that we'd find lots of these things and we'd be able to pick which one we want to go to. And we searched and we searched and we searched, and we didn't find anything that we could go to. And eventually, the very first object we found that we could go to, that's what we did. So we discovered in 2014, just almost exactly a year before Pluto flyby. And the only thing we really knew about it when we discovered it was that it's this cold classical object. Its orbit is extremely low energy, very circular. So it has to be old. Nothing's happened to it. That's great, because that means it's going to be a pristine, primordial example of what the early solar system looked like. You can't find that anywhere else. It's what we want to see. Fortunately, it's extremely faint. If you're not used to astronomical magnitudes, it's a negative log system. So, you know, Sirius is like magnitude 1. You know, the dimmest star you've ever seen with your own eyes unaided is probably magnitude 10. Pluto is magnitude 15. This is magnitude 27. You can barely see that. So each of those individual images there, you can obviously see it with a bright green circle around there. It's a bit less obvious without the green circle. Each image corresponds to 150-ish detected photons from the Hubble Space Telescope. So this isn't really signal. This is noise, but it's the best we got, so we're pretending it's signal. And this is with a broadband filter without you know, blocking out different wavelengths of color. We tried to do some color observations, and we kind of sort of said that it was red. That was about as far as we could get. So that's where we're going. This is what we're doing to get there. This is the New Horizons Spacecraft. This picture is almost to scale. It's not as you can see, it's you know, 2 meters by 2 meters by not quite 3. Our power source is a radioisotope thermal generator. This is a lump of plutonium with a thermocouple glued to it. And if you think that's not very efficient, it isn't, but there is no moving parts. And it doesn't matter where you are in the universe, it still makes power. But it's less power than we had at launch. It's less power than we actually designed for, because there was a safety shutdown that meant that we didn't even have as much plutonium as we wanted. So we're basically, the launch we had 245. It's now down closer to 200, which is barely enough to run a laptop, but we're running a spacecraft off of it. And we have this 2-meter dish on there, and it means that our current downlink rate, maximum downlink, is 1.6 kilobit, and that's in fast mode. Sometimes it's slow mode, so it's half a kilobit. So you don't get data down very fast. You basically take all your data very quickly, save it on solid-state recorders, and then slowly stream it back down when you have the time. And the one-way light time is 6 hours. So there's nothing real time. Everything is pre-programmed, and you just have to program it right. And that's the problem. So basically, it's going to fly past, and it's going to. We knew it was going to fly past, but we didn't know when it was going to fly past. So the spacecraft, we can figure out where the spacecraft is very precisely with radios. So just using the bright, how radio bright it is, you can tell how far away it is. But also you can use distant quasars to figure out where in the sky it is. So we know where the spacecraft is to within a few hundred kilometers. And on the spacecraft, it's got a camera. It's a 8-inch telescope, basically. It's kind of a backyard telescope. And so we can detect the object, and it could detect the object as soon as August of last year, but it can only tell you 2 dimensions of the problem. It doesn't tell you how far away the object is, because we didn't know actually how bright it was. So that gives us, this B-plane direction, the plane perpendicular to the motion of the spacecraft very well, but we need the time of flight. And the only way we could figure out what the time of flight was by getting the best orbit we could from the Earth. And usually you get a great orbit for these things by having a long-term data set that you build up, and the more motion you have, the better determined the orbit is. With Pluto, it was discovered in 1930. So we were literally digitizing, photographic plates that were taken by the Soviets in the 50s, and that's how we got it to Pluto. But we couldn't do this with this; it's just too dim. So we had to take data starting in 2014 and just take it as best we could and get the most amount of information that we could. So it was not an easy problem. So if anyone has ever shown you a Hubble picture, you're like, oh, Hubble pictures, they're so beautiful and gorgeous. And this is what raw Hubble data looks like. So the blue circles are stars, and they're stars that were detected with Gaia, which is a European spacecraft that is currently mapping every star that it can see. It's a wonderful project. If you want astronomical big data, it is the first real astronomical big data of the 21st century, and it's a lot of other projects are building on top of it, including us. So we're using Gaia to figure out where all the stars are in the images. Each pixel on this image is about 40 milliarcseconds. So each degree is divided into 60 arc minutes, each arc minute into 60 arc seconds, and then you switch over to decimal and say milliarc seconds. Because that's how astronomy works. So they're 40 milliarc seconds, and that gives you the pixel scale, and you can see the object over there. If you didn't know what you were looking for, you wouldn't believe that there was something there. But this is one of the better detections. So that's what we had to work with. We got about 200 orbits, so about 200 of those sets over the course of 5 years. For each one, the first thing we did was figure out where Hubble was pointing, because the images are much better quality than Hubble's pointing knowledge from its IMU. And the units here are, again, all these milliarc seconds. So you can see we're getting the pointing knowledge to less than a milliarc second, so less than 40th of a pixel, just because we're using 100 stars and we know exactly what the shape of each star is. But the object is really dim. So we use the pointing uncertainty as well as the XY uncertainty in the image and add the two together, and that gives us the actual physical uncertainty for where the object is. And you can see we're getting it to, within about 10 milliarc seconds, so with a quarter pixel, which is not bad for as sketchy a signal it is. But you can see this is sort of Gaussian. You can kind of just take the standard deviation of this and just assume that that's a Gaussian model. This is not Gaussian. This is not Gaussian. And covariance is definitely not. So really, to model this, you can't just assume it's a Gaussian and run with it. You've got to actually take each one of these points and build up a kernel density function for it. So you're fully propagating for each one of these measurements your two-dimensional uncertainty. And that's really tricky. No one actually had ever tried to do that with an orbit before. So we figured out a scheme to do this. So this is these observations that we were taking beforehand, and then we built up a kernel density estimator. All this stuff was done glue code-wise in Python. Python is the best thing for just putting a whole bunch of libraries together, because it's just so easy to import things into it. And because of that, most of the astronomical processing libraries that have been written in the past few years are in Python. And it means that you can exploit things that are coming from other industries. So MC is a Markov Chain Monte Carlo code, and it's great to use. So if you've got some log probability function that you want to throw into it and some data to test it against, it will give you a probability cloud. It is really easy to use and really powerful and fully multi-threaded, which is very useful for this because it's very CPU intensive. So we take these measurements of where it is, and then you need an orbit integrator to actually say, what's the orbit associated with that? And that I coded up in C++. It's descended from some ancient code that I found that was in Fortran 77. And you know it's real code when it has inline comments about which for loops will properly vectorize on a Cray 1. And that also means you got real optimized code. So I was able to get the C++ running as fast as the F77 and then wrap it up with Cython. And I really like Cython for wrapping these things up. And it meant that I could just use all the other Python tools associated with it. So then that gives me a discrete cloud of probability. So I don't have one orbit best fit solution. I have a full cloud that's got all the uncertainty and all the sort of bumps and wiggles from it. And so we got that uncertainty, and we knew that it was good, but it wasn't quite good enough. And we wanted to get even better quality data. And we were already pushing Hubble to the limit. So what oh boy, it's not going to run very fast. We then started to look at stellar occultations. This is when KBO's passed in front of a star, it blinks out. We did we did one with the NASA Flying Telescope, but we did most of them on the ground with amateur class equipment. And what we're looking for is just up there, just the star to blink out. And doing this, you're basically using the Earth as a scanline imager. So each one of these horizontal rows is a telescope. Each dot is an image taken by that telescope. And you see, and the bright dots mean that there's no occultation. That probably means the wind was happening. All these ones here, that big lump there, we detected the object. So the length of the object there is about 30 kilometers. So you can see that we're detecting it at, down to a couple kilometer scale in the Kuiper belt. And there's no way you can do that any other way. And it was really cool that that actually worked, and we can do a lot more of that now. So how good do we do? Well, this image here, we're zooming through. That's a scan where we had to check. That was the hardest image that we could have taken. That was the image that we didn't think we would actually get, but we threw it in there anyway. And we got it. And you can see it's just barely going off the edge on the top there. So that was really good. Time of flight error was 30 seconds. We designed it to 150. So there's the mission website, and I'm done.